Good morning, everyone. Thank you for the introduction. I'm Chengpeng Wang, a PhD student from HKUST. And today I'm very glad to present our work on the database management system testing in the ATC. So this work is a joint work with Xiamen University, the University of Southern California, and Tencent. So at the beginning of this presentation, let me first give some background about the database management systems and the logical bugs. Database management systems, and we call it as DBMS for short, is essential in many modern enterprise applications. And obviously, such system is very important and is actually the security critical because any bugs underlying such system can cause very severe consequences. For example, on January 11, 2023, a DBMS bug resulted in over 9,000 flights being delayed. And also, such system is widely used because we notice that there are, for example, there are about 300,000 companies around the world using MySQL. So the importance and the prevalence of such systems motivates us to improve their reliability. And among various kinds of bugs underlying such system, the logical bugs is the most challenging one that is very difficult to be discovered. So what is a logical bug? Briefly speaking, a logical bug means that the DBMS can return the incorrect result set for a given SQL query. So let's look at this case example. Firstly, we create a table named T, and we have the one single column, C1. And we insert some value, for example, the -1 into this table. And now we want to do some retrievement. That is, we want to select some data from this table. So this statement actually has two subqueries. The first query selects some data, but actually the result is empty because we notice that the predicate in this while clause is always evaluated to false upon this table. And on the other hand, the second subquery can return a very large integer as a result. So obviously, the overall result for this statement should be, it's just exactly this one. But after evaluating this query upon some database such as OceanBase, the result is 0. So such inconsistency indicates that there should exist some logical bugs underlying such system. Actually, this bug has been confirmed and fixed by the OceanBase. So as you can see, the logic bug is different from the traditional software crash because software crash is very easy to be discovered. You can just observe the runtime status of the system. But for the logical bug, the system can run normally, but it can get the wrong result. But the users or the developers are often unaware of such existence of the logical bug. So to discover the logical bug in the DBMS, the key problem is to resolve the task article problem, which is what is the correct query result for a given SQL query. So actually, this is a very important and central problem in the area of software testing. According to our investigation, there are major 3 lines of work focusing on the DBMS testing and try to resolve the task article problem from different ways, including the differential testing, article-guided synthesis, and metamorphic testing. For the differential testing, their design is very straightforward but effective. That is, we don't know what's the exact correct answer or correct query result for a given query, but we have different implementations of the DBMS. So if we want to test the MySQL, we can use another DBMS implementation, such as SQLite, as a reference implementation. So if we fed the same SQL query to these 2 DBMS implementations, their result should be the same. Otherwise, at least one of these 2 implementations contains the logical bugs triggered by this query. So it's very simple, but it's very effective. But unfortunately, we notice that different DBMS implementations have different support for the SQL delglet. For example, it is invalid to use its not operator to compare 2 numerical values for the DBMS system MySQL. But such operator can be used for the SQLite. So in this case, we cannot construct such query statement for the testing. And the second line of work is called the Oracle-guided synthesis. Basically, they generate a table containing some data, and then they will select some specific row or tuple as the pivot row. And they will construct a very specific SQL statement such that the query result must contain such tuple as one of these, such that the query result should contain this tuple. So for example, if we select the second tuple in this relation or this table, and we can construct a well predicate in this way, then the query result for this statement should contain this record. Otherwise, this SQL has triggered the logic bug for this DBMS. So this construction is very interesting, but we notice that it cannot handle the expressive SQL statement. For example, if we have some computation upon some attributes in this table, for example, if we use some expression or user-defined function, we cannot examine whether this tuple contains in the final result because we need to model the semantics of this user-defined function or this expression in an ad hoc manner. But this process will involve very huge manual efforts. And the third line of work is called metamorphic testing, which is also a very traditional but effective testing philosophy in the software testing area. Basically, they try to construct two inputs such that their output satisfy a given relation, and we call it as metamorphic relation. This is one of the typical works. Firstly, they will generate some input, select from well statement here, and this statement is more likely to be optimized by the DBMS. And we assume that we get this result. On the other hand, they will construct another SQL query just to move these well predicates to set these well predicates as the selected value of these select statements. So the query result for the second query should contain 0 and 1 or 1 as their result. And more importantly, the number of the 1 should be equal to the size of the first query result. If the actual output violates such relation, we can claim that at least one of these two queries triggers the logical bugs. So this is also a very interesting construction. But this line of work can suffer the very high false negative issue. For example, in this case, this select statement actually triggers the logical bug. But if we just construct this query by moving these predicates as the selected value, we will find that this metamorphic relation is not violated. So in this case, we cannot safely conclude that this DBMS contains some bug triggered by one of these two queries. That is, the violation of the metamorphic relation is a sufficient condition, but it's not the necessary condition. So this is actually the false negative, can make the approach miss such bug. So let's sum up. The existing techniques all have their own limitations. Specifically, the differential testing cannot handle the direct problem. Oracle-guided synthesis cannot generate the express form of the SQL statements to test the system. And although the metamorphic testing can avoid these previous two issues, the equivalent-based approaches can make the approach efficient enough to detect the deeply hidden bugs. So in our work, we try to propose an advanced version of the metamorphic testing. Just try to generalize the equivalence relation to another kind of relation. Specifically, we notice that the query result of a SQL query is essentially the multiset. So very natural relation is the inclusion relation. So if we can generate the second SQL query such that its query result subsumes the original one or is subsumed by the original one, then we can achieve the over-approximation or under-approximation of the semantics of the original query. And such approximation relation can provide statistical oracles in our problem. So based on this key insight, let me illustrate our ideas by this example again. So in this case, we actually need to select some data from this table, T. And the having clause is just this predicate if y is not to 0. So if we want to over-approximate the semantics of the SQL query, what we need to do is try to weaken the selection condition. So one of the mutations is just to change it to true. So in this case, the query result for the second query should subsume the original one. But if the actual result violates such relation, we can know that one of these two queries triggered a logic box. So following this idea, we design our system, Pinolo, in this way. Firstly, we will populate the database tables randomly. And then we will utilize existing technique to generate some initial query seeds and apply a series of mutators upon the seed query to achieve the over-approximation and the under-approximation. By evaluating the original query and the mutated one and comparing their query result, we can check whether their result violates the approximation relation. We will also go back to the step 2 to iterate the whole process until the system reaches their time and iteration limit. And now I will give more illustrations about how we can mutate the seed queries. Specifically, our mutators can be divided into 3 categories. The first category try to mutate over some relations. So here is an example. If we want to achieve the under-approximation of the original query, we can just add the keyword distinct so that we can remove some duplicated values from the result. And conversely, if we have the second query with the distinct keyword, we can just remove it to achieve the over-approximation. And similarly, we can use some other set operations, such as set union, set intersection, to achieve the over-approximation and under-approximation respectively. And the second kind of mutator try to transform the predicates. So as you can see in the previous motivation example, we can just replace these predicates with false and true respectively, so that we can achieve the under-approximation and over-approximation respectively. And the last kind of mutator is more sophisticated, but it tries to mutate the operators in the comparison expression so that we can get stronger or weaker predicates in this way. So by applying these mutators, we can just traverse this abstract syntax tree of the query in the bottom-up manner, in the top-down manner. So in this case, if we want to achieve the under-approximation of the original query, what we need to do is to pose a stronger restriction over this table or values. But we notice that there is a not operator here, so we need to relax the condition guided by this not operator. So one of possible mutator is just to replace this greater operator with this one. And to evaluate our approach, we implement our system and evaluate the Pinolo upon the mature database systems. And we select some state-of-the-art approaches to make the comparison. And also, we quantify the impact of the randomness in the seed generation. Specifically, we select these four mature database systems, and we select PQS, no rank, and TLP as a state-of-the-art approach for the comparison. And for the first research question, we run our system for 24 hours on each of DBMS, and we found that our approach can discover 41 unique logical bugs, and 39 of them have been confirmed by the developers. And more importantly, among all of these discovered bugs, 23 of them have been regarded as very serious bugs. And 10 of them have been have existed in the system for over 5 years. So it can show that our approach can discover very serious and deeply hidden bugs. And for the second research question, we run our approach and some baseline approaches for 24 hours on the same DBMS settings. And our approach can discover 41 bugs, but the existing technique can only discover 14 bugs in total. So the reason is that our approach do not have very strong restriction on the SQL statements, do not have very strong restriction on their syntax. But existing efforts can only generate very restrictive form of the SQL as input. So this can make their approach cannot reach very high coverage in the testing process. And we also measure the coverage data in our evaluation. So if you want to know more details about the coverage, you can refer to our paper. And lastly, we try to quantify whether the seed query generation can affect the final results. So we utilize the existing tool, Go Random Gen, to generate the 5 different initial seeds and run our system for 24 hours. And we found that under all the settings, our system can generate, can reproduce a bug for over 40 bugs. So you can see that such randomness will not have the big impact to the overall effectiveness and performance. And lastly, I want to give more discussions about the limitation. In our work, we still restrict our query should be satisfied given syntax. Specifically, we do not consider these advanced features of the DBMS. For example, we cannot generate the SQL with aggregate function, window function, or some left and right joins. For example, if we consider the aggregate function, such as a summation here, if we relax this selection condition, this while clause to be to get this weaker predicate, we don't know whether this query will generate a larger or smaller result because it's totally dependent on the content of this table. As you can see, if there is a negative value in this table, actually we can get more tuples, selected values, but their summation will be decreased. However, in our approach, our mutation is independent to the content of the database. So this can be one of the further directions, try to generate some queries and database content simultaneously to provide a reliable task oracles. And to sum up, in this paper, we introduced a very interesting concept that is approximation relation to resolve the task oracle problems in detecting logic bug in DBMS. And also empirically, we have discovered 41 logical bugs in 4 mature DBMS systems, and 39 of them have been confirmed by the developers. Okay, that's all for my presentation. If you have any question, I'm glad to take it. Thank you.